Hello everyone! Today we are going to talk about checksums. A checksum means a numerical value calculated from binary data using an appropriate mathematical algorithm. This can be used to identify changes in information. It is also a good method for researchers to use for data integrity checks. How can you know your files aren't corrupted? When doing research, integrity control is an important step in ensuring data quality and should be used as part of the data management routines. Data can be altered by mistake or intentionally. This can be done by humans or by machines and, I kid you not, by cosmic rays. Losing a single 0 or 1 can destroy the whole file. Bit flips happen regularly, while data quietly lies on a hard drive or tape somewhere. All media also slowly decay, which adds to this risk called bit rot. Especially risky are situations where files are copied or transferred from one storage medium to another, or packed and unpacked. This is why it is really a good idea to always keep your data in 1 or 2 extra copies, depending on dataset format, size, and value. And it is important to be able to track if and when changes have happened. To this end, we use checksums in data management.
In files, all characters, images, sound, and other information presented to the human user are stored as zeros and ones for the computer. This is called binary data. In checksum calculation, this binary data is computed to a checksum with a mathematical formula. If any of these zeros or ones changes, this mathematical formula will produce a different checksum. In this slide, you can see a checksum of a file listed in Etsin service. A checksum can be produced for a file for verifying its integrity in the future. When the checksum of a file is computed for the first time, it can be used as a reference checksum later. Afterwards, when the checksum of the same file is computed again, it is possible to compare it with the original reference checksum. If these sums are identical, then the file has not been changed. But if they differ, also the file has changed. In this example, we see a human-readable sentence in a text file and some part of its corresponding binary data. If we change just one bit in this file, or in other words, just a single 1 to 0, we can see that the resulted checksum will be very different. It is difficult to produce the same checksum by changing the bits, so therefore we can trust the checksum in order to say that the file has not been changed unexpectedly. There are several checksum algorithms, such as MD5 or SHA algorithms. All of these algorithms compute the checksum differently and will produce different results. Here you can see a couple of Linux and Mac OS examples for calculating a checksum. The tools for calculating checksums are typically found in Linux and Mac OS systems by default, but for Windows systems, separate software is needed.
Fair Data IDA is a storage service where data can be stored in an immutable state to preserve its integrity. IDA generates checksums for the so-called frozen files and stores the checksums as file metadata in its own database and in the centralized Fair Data metadata repository. The files are also replicated to separate physical storage so that if, for example, the file on the disk is corrupted by bit rot, there is another copy of the data available. Checksums for frozen files are generated automatically by the service using the SHA 256 algorithm and are displayed in the service as SHA URIs in hexadecimal form. You can generate a new checksum for comparison with the checksum generated by IDA by using the commands shown in the previous slide. But how can you know a file is corrupted? Well, this file you can easily see is corrupted. But what about this? Which one is the correct? This is why it's a good idea to have 2 or 3 copies of a data file and the checksum stored separately. Note that changing the file name does not change the checksum.
A checksum cannot be inside the file from which it has been calculated. If we alter the file by adding a checksum inside, the file will then change, and then the actual checksum is again different. Therefore, the checksum and its algorithm must be stored along with the content, but in a different file. One standard way is to use the packet format for your content. Minimal packet format defines a declaration file named packet.txt, a manifest file, and a directory named as data for the actual content. At minimum, the declaration file contains the version of the packet format used and the character encoding of the manifest file. The checksum algorithm is added to the name of the manifest file. So if it contains checksums created with MD5 algorithm, the name of the file would be manifest md5txt. The manifest file is simple. It contains the checksum and a file path, one checksum and file in each row, separated by a space character. The file path is relative from the root of the package structure. In Linux and Mac OS systems, the manifest file can be created directly with using the default checksum computation tools shown before. It is important to calculate the first reference checksums as soon as the files have been created, because it is not possible to follow the file integrity from the time period before the first reference checksums. If a file has been changed unexpectedly and the first reference checksum is calculated afterwards, then the file integrity is verified against the changed content. Since there is no tracking prior to the first reference computation, it is impossible to know that the file had already been changed unexpectedly. To follow the file integrity, the checksums need to be calculated and compared with the original checksums periodically, for example once in a year, and especially each time when the file is transferred or copied to another location. It is also good practice to add the checksum calculations and the integrity checks as events in the digital provenance metadata, including timestamps of these events. From this, one can see when the reference checksum has been created and how long it has been since the last integrity check. To learn more about provenance metadata, watch video number 5 about preservation metadata. As business as usual, the digital preservation services follow the file integrity and also fix the corrupted files automatically with managing several copies of the data.
This was the last part of our first set of guides regarding research data management practice that enable preservation. If you have any suggestions or ideas for additional videos on this subject, please be in touch with us. We would be happy to hear any feedback.